Thank you very much. Thank you very much for the invitation. It's a pleasure to be here for this day in the honor of Michel. So we met at several occasions in Rennes for conferences that he organized or for simple visits. And Michel always had a lot of topics to discuss and with a lot of enthusiasm. So it was a real pleasure, and I hope to have further discussions in the future. So for today, I will speak about some representation theory topic. So this is joint work with Karol Koziol. So I will start by motivating the study of this specific functor. So the motivation comes from the Satake morphisms. So so in this particular mod P setting. So I will fix a local field which will just be QP. In all what I will say, it could be some finite unramified extension, but for simplicity I will restrict to this case. So the ring of integers will just be ZP. And G will be a connected split reductive group over this ring of integers. And so the notation for this letter G will be the rational points, and taking the integral points I will denote it with a knot like this. And because we are going to speak about parabolic induction, I also need a parabolic, so I will just restrict to the case of a Borel. A Borel subgroup with its unipotent radical and torus, and again same notation for taking the f points. So B ut and B naught u0 t0. So that's all for the base field, and for the coefficients of all the representations I will look, it will just be a field of characteristic P. Okay, so in this setting, so the Satake morphism has first been defined by Herzig. So it takes the form of the usual Satake. So it's a morphism of algebras from the spherical algebra attached to this data, so which concretely is just given by the functions finitely supported on this double cosets, so functions with coefficient in K, and the ring structure is given by the convolution product. So it's a map which goes from this algebra for G to the same algebra but for the torus. and which is given explicitly by the same formula that we have with coefficients in C. So we need to associate to a function here, a function here. So I will give its value on an element T. So it will just be given by summing over the unipotent orbit of this element. So it's the sum over the TU, and U is in in this discrete quotient. So it's a morphism. Of K algebraic, so similar to the Sata K. Over C, so it's not exactly equal because there is because of some normalization which over C, which involves some power of P or P inverted that we cannot do in this setting, but nevertheless it allows to define Sata K parameters to any element here. So it gives Sata K parameters for the dual group with values so the dual group via the fact that this is just the co-characters of the algebraic torus, but so also the character of the dual. So the dual parameters appear at this level. Okay, so after that, Enier and Vigneras reformulated this map in a more functorial way. So namely to any smooth representation of the compact group, they associate a morphism which now takes the following form. So here we have the compact induction of this representation of G0 to G, and we take the endomorphism ring. So if we just take the V to be the trivial representation, this endomorphism ring is just isomorphic to this convolution algebra. So the target will be something generalizing this, which will be the endomorphism of now the compact induction from T0 to T of V, but after taking the co-invariance. The co-invariance with respect to the unipotent that we fix at the beginning. So again, for the trivial, so it gives back
You mean or U0 or U?
U0. U0. Thank you. Yes. Okay. So in this more functorial perspective, this map is constructed using some adjunction, as we can already see as it appears here by taking this co-invariance. So the construction uses an adjunction. So between this co-invariance and the parabolic induction. So here, this functor from the representation of the torus to representation of G is a parabolic induction. And the other one, taking co-invariance after restriction to B, is a so-called Jacquet functor. Okay, so this put the Satake morphisms into this adjunction. So now, if we want to go further, we note that since we are with mod p coefficients, the functors involved here are not exact. In fact, this one is, but this one is not. So we lose some information by only restricting to this abelian categories. So this is only right exact, sorry. But it's not obvious how to derive this functor, just because there is this very recent negative result from Schneider and Sorensen, which was in the folklore, but this is just a result from this year, that this category does not have enough projective, but in fact the only projective is 0. So the only so that's why we cannot apply easy computation for the derived functor, but nevertheless, so Heyer in 2022. Oh, I will maybe change the blackboard. Showed that this adjunction extends at the level of the derived categories. So, so the statement is as follows. So the T exact parabolic induction so as this functor is exact, it can be derived trivially just by the same formula. So here the dt are just the derived, the triangulated derived categories. So this T exact parabolic induction admits a left adjoint. So that it denotes in this way. And so to make the connection with the Satake morphism, I am adding that there is a similar adjunction holds at compact level. So and now, because we have this derived functors, we can extend this construction, but to some higher co-invariance in this sense. So in particular, for all I, so now it's we will have new derived functors in this interval. So not only in degree 0, but also in this whole interval up to the dimension of u. So here it's a dimension as a p-adic Lie group. So because I suppose that f was just qp, it's also the algebraic dimension of u. So for all I, we get a morphism. So first, bifunctoriality. So also for any representation. So first, we apply the derived functor of degree I. So we end in L I u of this compact induction, and there is a compatibility between the compact level and the full level, saying that this is also isomorphic to this. And so here, if we look this map at I equals 0, we just recover. So this is for I equals 0. This part is just the co-invariance that we had here, u0. Sorry. But now we have a family of all morphisms. So in degree 0, and actually also in the lowest degree, it's there is some duality between the top and the bottom degree. It is just the Satake map we had before, but in between there are a new family of Satake maps. So some kind of higher Satake maps. So this result of here is already quite satisfying, but there was another generalization in another direction of this initial Satake map in the following sense, so which is due to Ronchetti.
Are these Li finally sort of derived functors of the Jacquet functor?
So they are in the sense that this complex in degree 0 is the co-invariant, right. And I'm just taking so this is a complex, and now I can take the cohomology in higher degrees. So in this sense, they are the derived functors.
Can I compute this derived factor for you by approximating you by compact subgroups which are profinite, and then reducing from profinite to finite, and
so the way this adjunction is proved is by a broad representability.
Okay. You don't get some standard complex that computes the LU0.
The computation is not given by the construction. Precisely the goal of the talk will be to compute it in some particular cases. Yes, so the other generalization, which was a few years before, was that here we are still looking at ring homomorphisms, but here there are usual rings in the sense of non-commutative algebra, but there are rings. But one could also look at graded rings or DG rings, and this has been considered by Ronchetti, who constructed a morphism of graded algebras. So now I will take the X. So the endomorphism, they can be thought of home from the representation to itself. So X0 from a representation to itself. But then you can look X1, X2, or any higher Xi. So you can look in this direction. So Ronchetti only considered the case of the trivial representation. And he constructed a morphism in this way of the following form. Okay, of graded, yes. Okay, and after the work of Ayer, the question of relating this kind of generalizations to the others was still left, and so the motivation for this work was to try to understand the relation between these two generalization. So the question was a basic question: what is and so the answer will be given by actually computing the value of this just this representation of the torus in some specific cases that will include the case of the trivial representation. So the answer is that we will compute so the LIU of this representation, and even slightly more general ones that will come after. And so before explaining the computation, so the consequence for this morphism is the following. It will imply some orthogonality relations between what happens in different degrees. So it will imply that there is no extensions between what happens in Li and what happens in Lj for I different from G. So
So there you swap G0 and G.
sorry?
G0 and G.
On T also.
T?
No, you switched the two, the end from G0 to G and not from G to G0.
Superscript.
But that's okay.
Sorry. Thank you.
On the same before.
Yeah, and also on the blackboard above, you switched.
Sorry. Thank you. Okay, so there will be no extensions. So this means that now, so
For I distant from J.
yes, precisely for I. Thank you. Different from G. So it will only the diagonal terms will survive, and that's why we will get some this graded algebra morphism. So if we apply, so now I'm starting with this. So I'm just applying the derived functor L. so LU to this. And so because of this orthogonality, this will just be the product over the diagonal entries. So E from minus dimension of U to 0 of the X of so the corresponding, so that I will write directly in this form. Yes, Li. Li. Yes. So here I should have written just I'm keeping the diagonal Li, but I'm also using this the same this commutation of Li with the induction. Is that okay? So so now if we only look what happens in X0, so we precisely get this family of morphism, which are the endomorphism of the usual rings. And in this product, if we only look what happens in I equal to 0, this is the graded morphism of Ronchetti above. So this is how the two pictures can be put together. So that's all for the motivation, I think. So now I will go to the computation of these objects. So the computation will come from a computation in Lie algebra, actually. So we will forget about smooth representations for the moment and make a small detour to Lie algebras. So now G will denote the Lie algebra of the algebraic group mod P of its spatial fiber, and U, small u, will be the Lie algebra of the unipotent, and L0 will be the trivial representation of G. So the K input, the K computation has been done 20 years ago by Polo and Tilwin. And it goes as follows. So assume P is big enough. So here H is the Coxeter number of the root system. Then they can make the analogous computation of derived co-invariants, but in the setting of Lie algebras. So they prove that the cohomology, so here I'm taking cohomology instead of homology, but it's not a big difference. So the cohomology for this Lie algebra of the unipotent, of the trivial representation in degree I is given by the sum of certain characters. So I want to see it as a representation of the algebraic torus mod P. So it's the sum over the elements of the Weil group of length I, and the characters are the conjugated under the dot action. So where the action on characters is given by so it is a usual twisted action from representations of Lie algebras. And in fact, the right setting for this result is slightly more general than just a trivial representation. It is actually to take any P small weight. So more generally, they show more generally the same result holds for any L lambda, so still the irreducible representation of highest weight lambda with P small, so which means that lambda plus rho is less than P for all alpha among the positive roots. So the result is the same. So in the sense we replace 0 by lambda in the formula above. Same result holds. Just take 0 by lambda. Okay, so because yes. So because this is a K computation, I just mentioned some ID. So in fact, if we were not working mod P but over C, this is an old classical computation of constant. So over C, this is a theorem of constant. And a posteriori, now that we have the BGG category, so the Bernstein-Gelfand resolutions, it can be seen in a transparent way. So a posteriori, it comes from the BGG resolution, which is something like this. And so on. so up to the last element. And so here, so this is our irreducible representation. I could have taken any dominant co-character here, a character here. And these are just the Verma modules, so freely generated by the character. These modules are just rank 1 over the enveloping algebra of the opposite of U. So if we were interested in computing homology, we were just tensoring by the trivial character of this enveloping algebra, and so these constant terms appear just as the remaining highest weights.
So, by the way, don't you need lambda dominant here too?
Yes.
This is a plus. Okay.
Yeah, sorry. Yes. So it can be read off directly on this BGG resolution. And now what Polo and Tilwin prove is that such a resolution, which is a priori so defined over Q, it extends at the resolution over ZP. So it admits an integral form of the same kind. So now this, what Polo Tilwin prove, that this resolution in the space, so here there is no p-smallness assumption, only dominant, but in the p-small case, this resolution extends over ZP if lambda is p-small. Okay, so it's a it's a question about Harish-Chandra central characters, and they show that there is no congruence mod p in this range. Okay, so that's all I wanted to say about this, but I wanted to say a little bit because this is where we are seeing these characters appearing. So now we can come back to our original question, so which was about smooth representation and not about Lie algebras. So what remains to prove is some comparison theorem between Lie algebra cohomology and continuous cohomology mod p. So recall that we wanted to compute, say, so Li mu of this. Okay, so we can focus on this. So first, to make more precise the connection between this functor and some derived functors of the Jacquet of the co-invariance. In fact, when we are at a compact level, this comparison is completely transparent. So it's easier in that case. We have the following formula. At least if P is big enough. So it was h minus 1, here now it's h plus 1, but okay, so in that case, the functor we are interested in, so LU0, is really the cohomology and no more the homology up to shift and twist. So this is the cohomology of the unipotent. So this is a notation to say the cohomology complex of the unipotent. So shifted by the dimension of U and also twisted by some character. So here we had this rho. So 2 rho is something which makes sense. It's an integral. It's just the sum of the positive roots, and we can reduce it mod p. So we can consider this character, and so this is how we can compute it at compact level. So now what
did you write? Oh, on the right.
2 rho. So the sum of the as elements as representation of the compactors. Yes. Okay. So now what we want to compare this cohomology groups and this cohomology groups for particular coefficients. So a priori we are interested by the trivial one, but thanks to the computation of Polar and Tilwin, we can even consider the p-small case. So it's a comparison between continuous cohomology and Lie algebraic cohomology, so which sounds really reasonable. But because we are mod p, there is no general theorem that we can apply directly. We need to go a little bit in the theory of p-adic Lie groups, into Lazare theory of p-adic Lie groups to produce a priori a spectral sequence. So a spectral sequence going from this Lie algebraic cohomology to this continuous cohomology, and the result will be that it degenerates. So that's why at the end we have a comparison. Just to formulate this spectral sequence, I just need to introduce a bit more notation, but it's just to introduce this sequence. So this makes use of Lazare theory. So we have to use that U0 is p-valued. So the group U0 admits a p-valuation in the sense of Lazare. So this is a non-commutative version of usual p-adic valuation. So it is given, so it is characterized so because we are with the unipotent, we have the root subgroups, one for each positive root. So we can look what is the restriction to some root subgroup. So this will just be a function going a function like this. So taking an element x, we can take its p-adic valuation, but here so that it satisfies the axiom of p-valuation, we cannot just take this. We have to add some terms which depends on the root, which is the height of the root divided by h. this ensures that this is a p-valuation, in particular that the group is p-torsion free, so it is a Poincaré group, and so on. Okay, so this factor comes, so it takes into account the non-commutativity of the unipotent. If the unipotent is abelian, for example for GL2, then the theory would be much more simple. But this p-valuation is not what is called equi-p-valued. So there is no general comparison for general valuation like this. And so with such a valuation,
what did you know? You said that the correction term I alpha is for the because of the non-commutativity.
Yeah, I can be more precise. Yes.
What is equi-p-valued? No.
Equi-p-valued would mean that it would be a valuation which would not depend on the alpha. Equi-p-valued meaning I have a basis of the group, which each element has the same valuation. But here it depends. We have a basis given by taking 1 in each of the root entry, but the valuation will go from 1 over h to the highest root, to the highest height over h.
So the value is r bigger than 0.
R bigger than 0. Yes, its value is in strictly positive and infinity.
So here you use in the previous talk there was a multiplicative convention for valuation, and now it's the additive convention.
No. It's just It's just the valuation. It's the usual p-adic valuation. So it's 0 on 1 and it's 1 on p.
Ah, okay, because in the non-Archimedean...
Yeah, sorry, it's not a valuation as in adic spaces. It's a...
Valuation in like in algebra books. Okay.
Yeah, as in Lazare theory. Yeah, I'm sorry for this. One could call it a p filtration. It is, but being a p valuation is satisfying some more axioms than just being a filter. So this is Lazare's terminology, but it's not a valuation in the sense of the previous talk. Okay, and so yeah. So what is the fundamental result of Lazare? So is that this filtration or valuation induces a filtration on the Iwasawa algebra of the group. So omega induces a filtration on say K. So the Iwasawa algebra. And the graded of this filtration makes appear the Lie algebras, more precisely the enveloping algebra of the Lie algebra, such that the graded for this valuation of this Iwasawa algebra is the enveloping algebra of some Lie algebra attached to by Lazare again to this group. So this Lie algebra is actually the graded of the group itself, because we had a filtration on the group, so we can take the graded. It becomes an abelian group. It was a p valuation, so it's actually a fp vector space, graded fp vector space, and there is a Lie bracket coming from the commutator of the group. So this produces a Lie algebra, and Lazare had this comparison. So the graded of the Iwasawa algebra computing the continuous cohomology is actually given by some Lie algebra. So, of course, this Lie algebra depends on omega. So a priori, it has nothing to do with the Lie algebra, the algebraic Lie algebra we had before, just above, U Lie of UFP. But precisely, this precise choice of valuations makes things so that the Lazare Lie algebra attached to this omega with its Lie bracket is isomorphic to the natural Lie algebra coming from the algebraic situation. Okay, so this is part of the, this will be part of the statement. So before saying this, so because we have this filtration and this grading, this can be extended to complexes to produce this spectral sequence I was talking about. So this is due to Sorensen. So after the work of Lazare, so it's more recent. I don't remember precisely, but something maybe later like this, something like this. So then the omega induces a spectral sequence so which has the following form. The first page is given by Lie algebra cohomology. So what is, let's try to write something. So some graded of, so the complex used is the standard Chevalet-Eilenberg complex of the Lie algebra. So it can be graded, so the Chevalet-Eilenberg complex of the Lie algebra of Lazare with coefficients in the graded of the representation. So we take now a smooth representation of U0. So its grade, it becomes a module over the Iwasawa algebra, and so it's graded with respect to the filtration, which becomes a module over the Lie algebra. So this complex makes sense, and so there is a spectral sequence from this to the continuous cohomology we are interested in. So this is of this kind. So a priori, so it converges, but we only know that it degenerates after at some page which is related to this valuation. And for example, in the equivalent case, it always degenerates at the first page.
So what is a GRE? E1ST is H. There's a before the, yeah.
So here.
Yes.
So there is a, so using so this complex can be filtered, and this is the graded the number S of this complex.
And what is GRE V? What is the filtration on V?
And V, so so V becomes a module over the Iwasawa algebra, and then there is a filtration by two-sided ideals coming from the omega, and we just take the ideal of this filtration, so the adic let's say VEI. Okay, so in general, so it degenerates a priori at page R, which in this case would be essentially H. But in the equivalent case, we would add for free that it always degenerates, but because we are, say, with GLN, it a priori only degenerates at the nth page. So for an arbitrary representation. But because we are in a very specific algebraic situation, it will actually degenerate at the first page. So this is the comparison I mentioned. Here maybe. Okay. So now if we put everything together, we end up with the following. So assume P is bigger than h plus 1. Take lambda to be P small and consider V to be L lambda. So first, it can be seen as an algebraic representation of GFP, sorry. But from this, we can first take FP points, so it becomes a representation of the finite group, from which we can inflate to smooth representation of G0, and we can also view it as a representation of the Lie algebra now by taking the adjoint representation. So the result is now, so for this specific V, the spectral sequence so it degenerates at the first page. And moreover, so the data from Lazare theory match with the algebraic data. So the Lazare Lie algebra is isomorphic to this U, and this Greux omega V is isomorphic to this adjoint representation of L lambda, and so in particular we can compute so the cohomology we wanted becomes
so what is the adjoint representation of L lambda?
Sorry? So the representation of the Lie algebra derived from the algebraic representation.
Okay.
In particular, this is the same as a representation of the Lie algebra, so which was given by the previous, so this sum lambda. So more precisely, so this was an algebraic computation. Now we are back to the situation of smooth representation. So this has to be understood as representation of T0. So which means that this algebraic characters has to be evaluated on the sections and then taken mod P. And it can happen that, so all these algebraic characters are pairwise distinct, but it can happen that after restriction to T0 and reduction mod P, they collapse to the same. There is a small congruence. So a priori, I have to take here some semi-simplification, but it only happens in very few extreme cases. So this can be avoided. So this all without semi-simplifying, so can be avoided if, say, we are not equal to P minus 1, so lambda plus rho. Okay, so in this case, so all the characters are distinct. So in particular, in each cohomology group, we have distinct characters of the torus. That's why, as announced at the beginning, there are no extensions between them. We had this orthogonality relations, and so we have this clean way of producing the derived Satake maps. So that's all.
Other questions or comments?
Concerning the P smallness condition, so if you compare to representation theory and characteristic 0 with the Weyl character formula, what is the smallest condition on lambda for which it is like the reduction mod P of the reducible is still irreducible?
So it's precisely this one, to be P small. So an algebraic representation will remain irreducible mod P if the dominant weight is P small, if and only if.
If and only if.
Yes, yes.
Other questions? No more questions? Okay, so we'll resume in something like 13 minutes, I think. No? 12 minutes. I said 13, it's 12, but maybe it took 15 seconds between our two sentences. Okay, so we thank the speaker again.